All right, let's get a full screen. All right. Get the hair, mat it down. There we go. Taking off the winter hats these days. All right, so I'm hoping I don't ramble too much in this video. Going to be talking about reflections, derivative of inverse functions, odd and even functions, just a little bit of something here and a little bit of something there. But I want to get some of these thoughts in front of folks. And a lot of times we formalize some simple concepts and the formalization makes it difficult to understand. So I'm hoping that in this video, I can talk about how to graph reflections around a given point. So I'm going to talk about how to write that equation in 10 seconds or less, and then a bit of a reflection in that direction in 10 seconds or less. And we'll do a logarithm for a little practice. And hopefully be able to use a little geometric representation to simplify this whole notion of a derivative of an inverse function. All right, so let's have at it. So let me get my eraser and we'll start here. So this is a square root function. Let's actually go down here. I've got some things on the board already. So what is a square root function? It's important to know the trajectory, and I'll come back to that in a moment. So I've drawn a couple of squares. No area, area 1, area 4, area 9, and their square roots. I wanted to say that quickly. Square roots are side lengths of a square. That's where it comes from. And so I'm working with some easy numbers. The square root of 9 is 3. Okay, and then I decided to square 3.001. Don't need a calculator. There's patterns, 9.006001. Could have put more decimal places in, and you're going to get that first 3 matching this first 3, or first 10 decimals matching 0.0610 decimal places. So it looks like it's about a 6-to-1 ratio of change. And that change is the change in area divided by the change in the side length. And I did it over a very short distance. And much of calculation is linearization. And so I've really done y2 minus y1 over x2 minus x1. That's what I did. And I just did it over a very small distance. And I get a little feeling for change at an instant. Now, what's the inverse of that? Well, the inverse of that is going from the area back to the side length. So the area was 9. It came from a side length of 3. Well, therefore, 3.001 side length generates 9.006001. And we can look at the change in area. I'm sorry, the change in the side length divided by the change in the area. And of course, I can multiply both of these by 10, 100,000, 1,000, and I get a 1-to-6 ratio over here. And over here, 0.006. Yeah, you can see that, right? Same thing would be 6-to-1. Well, they look like reciprocals to me. Interesting. And why would we get reciprocals? Good question. Well, how do you get the inverse of a function? I think you change the x's and the y's. And if we change the x's and the y's, we got an x2 minus an x1 over a y2 minus a y1. That's something to think about. Okay. And let's get back to what that square root was over here, what the square root. Oh, I guess I should graph a little bit of the relationship. Okay, over here, we've got, and I'm just looking at the left-hand branch. Guess I got to come here. Yeah, I told you I was going to ramble in this. Okay, but we went from 0, go over 1 unit, up 1, go over 2 units, up 4, go over 3 units, up 9, and we can see the right side of that parabola. All right, and what's the inverse of that going to be? Well, it starts at 0. All right, I lost my diagram. Over 1, up 1. Over 1, up 1, but the square root of 4, big jump here. Only a unit change of 1 here, but now I've gone from 1 to 4, 3, gets me 2 units of change, and then 9 goes to 16, which is, what did I miss? 4 goes to 9, which is 5 units of change. It looks like the next one's going to be 7, so on and so forth, and we get the trajectory of a square root function. All right, so now, yeah, this is not the best video ever, but we're moving around. So how do we write this one? let me just write -117 here, so I don't have to think about that again. So, well, I think I'm measuring change from 5. All right, if there's a pattern here, it's emanating from x equals 5. That's the input. And I see a general trajectory of a square root, so I can change the parentheses, use the square root, acts like a grouping symbol. And then when I put 5 in, I get 0, which is, where you can't take the square root of negative numbers on the Cartesian coordinate system. Certainly, there are things you can do with it. And I want 7, I got the marker, so now I've made the input of 5 act like an output of 7. And I need to look at the square root change from 5 to 11, which is the square root of 6. And 7 to 17 is 10 units of change. So if I put that in a graphing calculator, this would get me that graph. And that's useful to know. I didn't have to do any algebra. I didn't have to plug something in and solve anything. I can see the change of rise over run squared as measured from the endpoint. Okay, now I want to start talking about reflections a little bit. What if I wanted this to go in the other direction, where it passes through -117? All right, I'm looking the other direction. I should be able to write that. There's a pattern. And so we'll write that in a second. Let's look at this. Probably should have put these notes in a different order, so I wouldn't be having to walk around the room like this and have you have to kind of follow me along. So I'm looking at y equals x minus 5 and y equals 5 minus x. Now, most Algebra 1 students would recognize x minus 5 as a y equals mx plus b, and I wish they didn't, because it gets the way in teaching higher level concepts. Right? The real important number here is 5. However, it's much easier to teach, plug a 0 in and get -5 and get the y-intercept. All right? But when I plug a 5 in, I get the x-intercept, and that's far more interesting. 5 gets me a 0, and I go from negative to positive numbers. And this is called a root. So it would be nice if we put parentheses around that and measured linear change from 1 or linear change from 5, if it was an exponent of 1, or squaring change from 5, or square rooting change, which could have been written as 1/2, so on and so forth. We would be looking at an entirely different process at the Algebra 1 level if we did that. And I'm in favor of that. Okay, now, if I did look at x minus 5, it's that line, right? But if I look at 5 minus x, turns out it's very similar line going through 5, 0, except instead of going over 1 and up 1 as a ratio of change, I'm going back 1 and up 1. Bit of a sign change there. All right, so let's play with that now over here. Because there was a reflection around x equals 5 over there. So how would I write this? Well, I'm looking to that direction and I'm measuring from 5. Then I'm going to say 5 minus x. And I'll take the square root of that. All right, and what's from 5 to -1 is a change of 6 units. 5 minus a minus 1. Square root of that, well, that's square root of 6 again. And I'm going from 7 to 17, which is 10 units. Of course, I got to put the plus 7 here. And I can look at what are, in essence, reflections. When I looked at x minus 5 over there and thought of it in the mx plus b, well, really what I was looking at was change from the number 0. And we don't write that. A little bit confusing when we start talking about when we have graphs that shift. Well, they don't really shift. We're just measuring operational change from a different x value. And I think that's what needs to be stressed. So let's actually do another one. Random one here. I put something up a little while ago. All right, so you can pause the video and see if you can write that. All right, so this is just a square root again, and I'm measuring from 3 and I'm measuring in the positive direction. So I write x minus 3. I want 8. I put 8 in. I go from 8 to -15, which is minus 23 units. Rise over the square root of run, and from 3 to 20 is 17 units of linear change, but I'm looking at square root change. So if I put that in a calculator, I've got that graph. Now let's go in the other direction, some random numbers. How about we start with 2, 5? All right, let's go this way. All right, let's go to, I don't know, how about 19? Oh, no, I'm going backwards. No, negative 19 then. Negative 19, comma, something below 5. How about minus 11? All right, so I'm measuring from 2, but I'm measuring in the left direction, so I'm going to say 2 minus x. Square root, I want to get a 5 attached to the 2, and the smallest square root I can get is the square root of 0, so it's, I'm going to measure from there. And now I'm making 2 act like a 0 if I plug it in. 2 minus 2 acts like that 0. And I'm looking at linear change of 21 units to the left. But when I put minus 19, the opposite of negative 19, I get 2 plus 19, right? When I do 2 minus a minus 19. Hope you can see that. So I've changed by the square root of 21. And I don't think I want to change by the square root of 21. Because I don't think the square root of 21 plus 5 takes me to negative 11. I don't think that's true. But I think I can get to negative 11 if I change by 16. Oh, I got to change by negative 16. Sorry, I'm going down. Negative 16 plus 5. There we go. And I guess I got to get rid of that square root of 21. Principle of conversion. Piece of cake, done. It usually takes a couple of days of practice. A couple of minutes every day. Most students own that. After about 4 days, it seems like the magic number is 4. So I would suggest you look at the video for 2 minutes, 4 days in a row, see if it works for you. And then we'll take a look at a reflection of a logarithm. Random numbers here. Let me put some random numbers in. Let's let x equal 2. I did 2. It's in my head, I guess. Let's go over here and say at negative 1, we get, how about 1800? And at negative 7, let's get something above 1800. How about 2024? And let's see if we can write that equation in 5 seconds or less. Make some room. All right, it's a little easier this time to start with the y values. So I'll start with 1800 and then ask the big question, how do you get to 2024? Guess you got to go up 224 years to get there, and it's a logarithm based on 2, so x minus 2. I guess you have to have studied some logarithms at this point to follow what I'm doing. I'm basing my equation on 3 things. Log 0 is undefined. We'll just do that for now. Log 1 is 0. Real easy to multiply by 0. And log base b of b is 1. And it's real easy to multiply 224 by 1. So I'm really starting with 1800 plus 224 times 0, which will get me 1800. And then I'm going to do 1800 plus 224 times 1, which is going to get me my second y value. All right, but I already made a mistake here because I'm looking backwards. So I should have said 2 minus x. Little muscle memory. I always make the 0 because we're looking left now. So I'm not going to make the video again, running around the room too much. I'm getting dizzy. And so I'm going to plug in negative 1. 2 minus a minus 1 is 3. 3 divided by 3 is 1. And we know log of 1 is 0. So that's going to get me 1800. 0 times 224. Then I'm going to drop in negative 7. Minus a minus 7 is 9 divided by 3. I'm going to leave it as 9 divided by 3. Just I don't want to write the same number in any initial video. I want to get some difference there. So let's change this to minus 8 on the fly. Let's change this to minus 8. So go back here now. Minus a minus 8 gets us 10/3. All right, and then that's that video. That's that equation. All right, I better get a coffee in me. Okay, just wanted to put some things. Oh yeah, and so we often talk about odd and even functions, all right, which are really kind of the first look at reflections. But we don't write f of x minus 0 because these reflections are all based on the y-axis, right? And we talk about odd and even, probably because the first person to really consider this probably looked at the exponents, even exponent, odd exponent. And so all that means really is that if I put 2 in and square it, I get 4. And if I look at minus 2 and I square it, I get 4. I get the same answer. That's what that's about. And I get the opposite answer with the odd functions. So let's say we did this, let's stick with x cubed, easier to see. 2 cubed is 8. 2 cubed is 8. Minus f of minus 2 would be minus 2 cubed. Minus 2 cubed is minus 8, but I'm doing what? Taking the opposite. And so that's really measuring from x equals 0. I don't think you have to measure from x equals 0. I think you can talk about reflections from other axes, but it wouldn't be a formal definition. Maybe it would. I don't know. I don't see any reason why we couldn't have done what we did over there. We could do x minus 5. And I'm just thinking about this on the fly. And 5 minus x, I'm talking about odd and even based on a reflection from a different x equals axis. Something to think about. All right, so I just was mulling that over a little bit. Not sure what I forgot to say. I always forget to say something. Yeah, I did have this on the board, so maybe I can at least make a passing comment about it. But, I believe if you have operational patterns that emanate from a given point, like the absolute value, like a square root, like a cubic, then you should be able to define very quickly and easily. I know I had to do it with a computer, x to the 6, x to the 7th functions, what the graphing form were. I didn't see any purpose in using them, but they exist. Whereas if you had a linear function, I don't think any point on a line is any more important than any other point. All right, so you can pick and choose. Same thing with exponential functions. Exponential functions, the only thing is you definitely have to have the asymptote defined, but it doesn't matter what 2 points you pick. So there's an infinite way of writing exponential functions. But I think we should be considering change from a given location earlier in high school education, math, and not put so much emphasis on y equals mx plus b. Oh my God. So a lot of students can't break the habit. They think every graph is a line. And I don't blame the students. I honestly think that some things need to change. All right. So just opinions. You can write and tell me if I'm off base. Feel free. Otherwise, have a good day.